Hello, welcome. So, someone recently asked if I could do some hydrostatic math. Hydrostatic. Hydrostatic math. And since this is a physics-based and physics-heavy concept, I thought that I would just kind of fast forward into where the math comes in. So I'm not really going to derive the two main formulas that I'm going to highlight today, but there are a whole bunch of variables, and so I think it is worthwhile. At some point I probably will come back to this, but it's probably worthwhile to really take our time to figure out where the equations come from, and we can really boil it down to Newton's F equals ma formula, and also some definitions with density and stuff like that. But I thought we could work through a specific problem today. Soft spoken, of course, so you're more than welcome to relax, and maybe even take a little nap. So, whether or not you are learning this in calculus, I think there's some really cool thought experiments in this, and so I'm excited to see if I can get anywhere with this problem. So the idea for hydrostatic math, we're trying to find the hydrostatic force or the hydrostatic pressure, usually. And what that is we are going to basically submerge something under water. Okay, and in this case, I'm going to put a rectangular plate down. So this might not be totally to scale, but that's okay. Let's see how much is this. Okay, so I'm going to put this plate underwater, and the idea here, the general intuition is that if you're in a pool, let's say, and you go underwater, if you stay near the surface, you don't feel very much. But if you swim over to the deep end and you swim all the way to the bottom, you might start to feel pressure. It sometimes even hurts your ears a bit. And so you will feel a difference, right? And basically that pressure it's like a force from the water, the weight of the water above you. So at the surface there's not much water, but deeper down you feel more water, more weight, right? So when you find the hydrostatic force, it's the force of the water on you, basically. Okay, what are the forces acting on this? It's the water on you. Okay, and so when I talk about a rectangular plate here, it's important to think about the orientation of this plate. So in this case, since I want to make this a calculus problem and we are going to be integrating, this plate is going to be vertically in the water. It's going to be placed vertically as opposed to horizontally. So you might need to try some of your own hand gestures here. But if you think about it, if it's horizontally, so let's just say it's horizontal and I just push it underwater, okay? Every point on that plate is going to be at the same depth, right? Every point is going to be at the same depth because it's horizontal and it's just pushed in, right? So that means that there is going to be one uniform force at each point there. But if I put the plate vertically down, you can imagine this top part, for instance, is going to be closer to the surface and therefore not have as much force on this part as, say, on the bottom. The bottom is deeper down, and so this will have more force. And so, of course, incrementally, that force will get bigger because there's more and more water acting on it. So, since it varies, we're going to try to calculate this mathematically. Okay? So, the two main formulas that we need for this kind of problem is that force equals pressure times area. And you might see this rearranged a little bit differently, like pressure is a force over an area, and that's the one that's more intuitive for me because it's a force applied over an area. So is how much pressure you have. But rearranging that, you get F equals P times A. And also, pressure is rho, which I'll get into, times G times D. So rho is the density of your liquid, and in this case, water. G is the gravitational constant, which you would expect because the force is going down. And D is your distance or depth. Some call it height, whatever you want. Okay. And, oh yeah, and so rho is a Greek letter. It kind of looks like a P. That's my drawing of it. But it's rho. R-H-O. Rho. Okay? Okay, so if I substitute P into here, right, then I just get F equals rho G D A. I wasn't kidding when I said that there are a bunch of variables. So I just substituted this P into that. Okay. but rho is going to be constant. It just depends on your liquid, in this case water. G is our gravitational constant. So now we really need to work with D and A, the depth and the area. So, like I said, if our plate were horizontal, so let's put some, let's put some units to this, or let's put some measurements here. So let's say this is 0.75 meters. This is, let's just say 2 meters. And let's say it is 1.5 meters, okay, to the top. So if I were to put this horizontally, then we said that every point, I can't really draw it because it goes into the page, right? But every point on that plate is going to be the same depth. So we could just plug that into D, and then we could just find the area of that plate. If it were a rectangle, we can just do length times width, right? And so we could just do rho times G times that depth times that area, and you're just multiplying 4 numbers, okay? But in this case, because it is vertical, we can't, because like we kind of started out by saying, the depth will vary in between, and we only know that the top part here is 1.5, okay, from the surface to that first, to the top, but then it increases right in between. So what area are we really talking about now if we're going vertically here? Well, instead of doing horizontal, we can break this up into a bunch of tiny rectangles. And that should be ringing some sort of bell as far as calculus goes. A whole bunch of tiny rectangles. It's exciting stuff. It's our Riemann sums, right? Breaking an area up into a whole bunch of rectangles, blah, 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 and adding them together, Riemann sums. So we can break this up into a whole bunch. For now, just an arbitrary height. We'll just call it delta y. But then, as we take the limit as n, which is the number of rectangles, as n approaches infinity, we're going to have a whole bunch of teeny tiny rectangles, and that will turn into an integral. That's what the integral is an infinite sum. So what we're going to do is find one arbitrary rectangle, find the force on that, and then we're going to add together by integrating. So that is what our A is, and that's what our D is. It's going to be the D at that particular rectangle and A of that particular slice. Okay? And then we're going to add them together. So, in this particular case, we have our delta y. So let's start with like the area part, right? We have a delta y, and then to find the area of a rectangle, you do length times width, right? And so in this case, we have a delta y, and then what is this thing, this horizontal part? That's actually 2. we're lucky because this is nice and pretty. It's a rectangle, so this is going to be 2. So the area is going to be 2 delta y, right? 2 times delta y. And I'm just labeling that as delta y. So that's our area part. And then let's do D. This part is tricky because, like we said, for this plate, that D varies. But this kind of, how do I measure that? It's not quite 1.5, but how much am I adding? What is this actual depth of this exact rectangle, this green one? Well, it's going to be 1.5 plus a bit, but how much? And so this is where we need to pick our own scale. So we need to label an X and Y axis. And this is up to you where you want to place it, as long as you are consistent with your own diagram. It's like a reference frame. So some people like to place it, symmetric. Some people like to place it at the top, at the water surface, so that Y goes down, negative. I like to place it, I don't know, I kind of switch it around, but for this one I would probably put it right here on the corner. I do like corners because it kind of automatically sets one part to 0, and I like that. Okay, so this would be X and this would be Y. Like I said, as long as you're consistent with with your own axis, when you take the integral, it'll work out. So in this case, now according to my axes, this part is going to be Y. So let me just highlight this so you can see better which rectangle I'm talking about. Just that little green sliver. Okay, so the little height of that rectangle is going to be my delta y, which I'm going to make infinitely small anyway. And the actual, from my axis up, it's going to have, this part is going to be y. So in order to calculate the depth from the top to my rectangle, that's what I'm trying to figure out, I'm going to need to use a little bit of geometry and just kind of picture what's happening here. But one thing is, it's 1.5 to the top, so this part's 1.5, and then the side is 0.75. So the total is 1.5 plus 0.75, which is 2.25 meters. And then, since this part is y, so I know this is kind of hard to see now, but that part is y, and the whole thing is 2.25. So that means the top piece, which is the depth that we're looking for, that depth is 2.25 minus y. Does that make sense? So I think it's more complicated looking when you draw it than actually just seeing what's happening. Basically, I set this part to be y. I'm looking for the depth of my green plate, so just this distance from the top to my green plate. But with the information given, I don't have an exact formula for that. I do know that the top of my plate is 1.5 from the surface, so 1.5, and I know that the actual height of my plate is 0.75. So the total from the top of the water, the surface of the water, to the very bottom is 2.25. But I'm going to let y be because according to my axes, I'm going to let y be the moving upwards, or the y distance, the vertical distance up. So like the rectangle could be down here, and that would have a smaller y, and then as we move up, my y would increase. So that means the actual depth of my particular rectangle is 2.25 minus that y. Okay, I hope that makes sense. So my depth is 2.25 minus y. And then rho and g are constants. Rho is the density of the liquid, in this case water. And since the units are given in meters, rho here is 1,000 kilograms per meter cubed. Okay, so that's just a constant. I forgot, I don't know off the top of my head the equivalent with feet, but when we do another problem, I'll try and make it a point to use the units for feet. But rho for water with meters is 1,000 kilograms per cubic meter, and g is our gravitational constant, and with meters it's 9.8 meters per second squared. Okay, so I'm just going to plug those in. So we have A, I'm kind of doing it backwards, but A, D, G is 9.8, and rho is 1,000. Okay, so this is the force on one particular rectangle, just an arbitrary one. And so now, like we said, we're going to take the infinite, the limit as n approaches infinity, so that this rectangle has a teeny tiny height, basically so that delta y becomes infinitely small. Okay, infinitely small. And we're going to add those together, which means we're going to integrate. And when we integrate, this delta y won't be delta y anymore. It will become dy. dy. Because it's infinitely small. And we're going to integrate, we're going to add y from 0 to 0.75. From 0, 0, because 0, where y is 0, to the top of the plate, which has a height of 0.75. The whole thing, because it's given as the dimensions, right? So this is where it's important to stay consistent with your axes. Some people like it in the middle, and depending on how you add, right, you might have negative to a positive, you might always have y as negative, but like I said, as long as you're consistent with your bounds and with your equation, the integral will work out to be the same. So I hope that we're good so far. We now have a definite integral. This is F, by the way, the force on the whole object. So we start with the force on one rectangle, then we take that sum, which turns into the force on the whole thing. So we have a definite integral, we have one variable, y, and so we should be able to just evaluate this. So I'm going to start by pulling out the constants, and take your time if you are learning integrals right now. So I'm just going to pull those out because you can. So 1,000 times 9.8 is 9800, times 2 is 1,900. 1.600, I believe. I'm kind of silly, I only have this calculator on me when I'm working with big numbers. That's okay, I think it can handle it. 1000 times 9.8 times 2, 19600. Good. So we are going to pull that out and then integrate the rest. So 2.25 minus y dy. So we have 2.25 y minus y squared over 2 from 0 to 0.75. And then if I plug in the top bound, that's just plugging in 0.75 wherever there's a y. And then I notice that if I plug in 0, this goes away and this goes away. So really we're just going to plug in 0.75. So 19600 times 2.25 times 0.75 times 0.75 minus 0.75 squared over 2. And this is where I kind of wish I had my scientific calculator, because at least I could, or at least a calculator where I can have parentheses. Because I don't know if you all are good at this, but I don't know what this memory stuff is. I never know. So I'm sure some of you are like whizzes with this, like, oh, boom, 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 but I don't know it, so I'm just gonna have to do it by order of operations here. 2.25 times 0.75 is 1.6875. Then minus, and then I have to do 0.75 squared. So 0.75 times 0.75, and then divided by 2 is 0.28125. So then 1.6875 minus 0.28125 is that times 9600. So I get 27562, so 27,562.5. And since we're talking about force, the units would be newtons here with kilograms and meters, so newtons, I believe. So let me just check those numbers really quickly. Okay, good. 1.6875, 0.75 times 0.75 by 2, and then, so I'm just going to do the negative version. 1.4065 times 1960. Yep, and I got negative just because I switched these two, just so I didn't have to retype it, but 27,562.5. Okay, I think we got somewhere. I hope it's correct. At least I think the logic and reasoning is fine. So we'll just try other shapes and see what we get for those and see if we're on the right track. If you have any particular problems that we could look at together, that would be really fun. I really appreciate topic suggestions, and if you already have left one, odds are it is on my list, and I am kind of working my way through. Even if you're not learning this stuff in particular, I will continue to fill in my playlists, so keep an eye out for that. Yeah, I think this is pretty good. I think we're on the right track here. Let me know if you notice anything like really obviously wrong. But just remember that this density, usually it's water for these kinds of questions, but if not, the rho will usually be given. And G will be 9.8 if you're using meters, and I'll write down the conversions for feet in case you're given, like a different shape with, 2 feet by 3 feet or something like that. And I think we've touched on what we're really talking about for depth and area, and whether we're talking about plates that are horizontal versus vertical. So when it's vertical, we're going to use some sort of integration most of the time, and if it's horizontal, usually we basically won't. We can just find the area, and the depth is constant, so we can just multiply. Okay, well, thanks for hanging out with me. I hope that this was relaxing and kind of fun, and I will see you around.